Yonglip, when you give your presentation, you must show your face, Yonglip. Right now, you don't show your face.
Okay.
Yeah,
I
okay,
will.
Dr. Jiva is going to join soon. And this Michael Chin Chong is still in the bus on the way back to his house in so he's controlling from the So Dr. Jiva, welcome to the presentation.
Okay, thank you.
So we are on the air now. So we will start at sharp 8:30 p.m. Okay.
All right.
Okay, Michael, we will start at 8:30 p.m. So, Michael, I think later on, Michael will edit it, so this will not be shown on YouTube lah, because there's some technical issue with the Facebook, so it's only on YouTube live lah. All right, yeah.
How do I share screen?
At the bottom there, you see there's a box with the arrow pointing up. That's the one.
Okay.
That's the share box. Once you press it, share screen, you share. And then if there's a person sharing you it earlier, he will unshare his screen. Then only you can share. And when you finish your presentation, you have to unshare your screen. Then the next person can share. Anything, let me know.
Okay.
Otherwise, normally Michael is controlled, but Michael is in the bus now from Penang on the way back to his house to Ipoh. Ipoh. So by the way, Yonglip, Dr. Jivaraj is also from Ipoh. A very long time amateur astronomer like me also lah.
Nice to meet you.
Hi, thank you.
Yeah. So Yonglip is back from his studies, university studies for holiday in Penang. He's back from China lah. Back from China. No, from Taiwan. So 1 more minute. Okay, a very good evening to people who are watching or listening on this program. All right. So this is again our astronomy picture of the day presentation by the Astronomical Society of Penang at the end of every month, right? So it's the end of the last Sunday of the month, which is the 25th of January. So we have here to present 3 members. So we are from the Astronomical Society of Penang. My name is Dr. Chong Hon Yu, and we have here with us Dr. Jivaraj Nadaraja, our key member from Ipoh, and our Tae Yong Lip, all right, and our member who is back from his holidays from Taiwan, is back in his hometown. So Dr. Jivaraj is in Ipoh, and I and Yong Lip will be from is in Penang, all right. And also hosting this what they call meeting is our member Michael, all right, in Ipoh. And the pictures in today's presentation for the month of February 2024 are selected by Mr. Lai, our member, all right. Also, so let me start with the first one, which is on the 25th of what they call February. So can you see my screen, Yonglip, Dr. Jiva?
Yes.
Yeah.
Yeah. So this is a nice one. Wow. Let me make it smaller. So Dr. Jiva, Yonglip, this is actually a replay. All right. Now this is of course written here. A Phoenix aurora over Iceland, 25th of February. Actually, this came up in I remember very well in March 2016, 8 years ago. All right, it came up. So it's actually taken by, I'll read below here, by our Mr. Hallgrímur P. Helgason, a kind of a landscape photographer in Iceland. All right, and of course it's processed by our famous American image processor, Judy Smith. All right, I think she stays in California. So basically, you see here, wow, this is aurora. It looks like a phoenix. It's a bird, and the rollover annotation is behind it. You can see the stars and constellation. So basically, in the information it says that sometime in September. He never say what year, but I suspect Mr. Helgason did it in 2015 because it was in September. It appeared in March in 2016, so it must first taken in 2015 in September. So he went to a kind of a dark location because being September means in autumn, so the sky is quite dark, and it's already they were waiting for the whole night, and they got quite fed up at 3:30 a.m. So a group of aurora photographers were waiting for aurora to appear, and at 3:30 a.m. everyone left except for one guy, the guy who took this picture, Mr. Hallgrímur Helgason, and this appeared in the sky just for 1 minute only. So you can see the phoenix, the bird there. Remember, phoenix is an ancient Greek folklore bird where you have the bird that was died and then turned into ashes, burned, and then from the ashes it grew up a new bird, a new phoenix, all right? And then there's the head, the beak, the right wing, the left wing. And actually you see here, and the rollover annotation by Judy Smith, we have the Orion constellation. Yeah, and you can see the stars, all right? And you see the pretty star cluster and so on. So basically, when you are in Iceland, which is close to the North Pole, when you see Orion, it's looking towards the south. That's why you see Orion is towards the southern horizon, the horizon. And you see here a mountain and a river. And this place is about 30 kilometers to the south of the capital of Iceland, Reykjavik. But the beautiful thing is, you look at the aurora, so nice, So it was so nice that it appeared first in APOD in March of 2016, and it appeared again today, all right? Because it's very famous. And you look at the Facebook of Mr. Hallgrímur Helgason, when it appeared in 2016, for that day, it was the most reposted picture in the whole of the internet, all right, on that day, all right, sometime in March 2016, all right. So I repeat, a Phoenix aurora over Iceland, a very lucky shot. They waited the whole group the whole night, couldn't see anything in the sky, no aurora, and all of them left except for one guy, and this appeared in the sky for 1 minute, and he got it. So lucky, I really like this picture, right? So I will unshare my screen there now. Yeah. So I pass to Dr. Jivaraj.
Okay.
Yeah.
Thank you, Dr. Chong. Now, all right. For my first,
Yeah. Share your screen.
okay. Share.
Below there, there's a box with an arrow inside the box. There's a white box, square box, and inside the square box, there's a arrow pointing up.
Okay.
That's the one. Got it? Can see and can hear.
Okay, good. Now, this is a picture of the globular star cluster 47 to Penang. It's taken by Marco Lorenzi, who, if you read about him, is a very interested amateur astronomer. Starting from the age of 14, he took his first snapshot using his dad's camera. And he has, over the time, he has become hooked on astrophotography. In fact, according to his page, if I go there, I see that he's now actually in Singapore. And he shoots most of his planetary images from his home rooftop in Singapore. But his deep sky, which you'll be surprised because you won't really be able to get this globular cluster taken so well from where we live because it's really further down south. And so he also says his deep sky images are taken remotely from observatories, which he manages in Australia first and then Chile. Now, these, of course, are very much down south, and you'll be able to see this globular cluster very well easily. He's had many pictures which have been selected for APOD, and this is one of them. And he's had 3 decades in astronomy, and he says that when he looks back about when he started up to now, he's amazed by the technological advances that has enabled us as amateur astronomers to take pictures which are actually really incredible. Now, coming back to this, this is a fantastic picture, isn't it?
Yeah, fantastic. Yes.
I'm very partial to globular clusters because I love watching them through. I was a visual astronomer mostly. I am, and I love looking at globular clusters through the telescope with your naked eye, so to speak. And this is one of the jewels of the southern hemisphere. It is the second brightest globular cluster after Omega Centauri, which can be seen from much easier from our places in the equator. It's about 13,000 light years away, and it's near to the southern Magellanic Cloud. I have tried it from looking at it from KL, but it's just about almost impossible because it's very low down to the horizon, and unless you got a clear view towards the horizon, you won't be able to pick it up. Okay. Now, it's made of course, we all know what globular clusters are. Hundreds of thousands of stars packed into a small diameter, in this case of a volume of 120 light years across. Okay. Now, there are red giants on the outskirts, which are the yellow ones. Again, a yellow this thing. And also you can see a lot of other blue colored stars. The center is too densely packed to be able to pick out. But what's interesting about this star cluster is now within this, according to the latest telescopes and all, using X-ray, the new Chandra X-ray telescope and so on, they have found a star which is orbiting the closest to a black hole and really spinning around with, I think, at a speed, or rather at how shall I say, at a time frame of about 48 hours or so. Okay. And they're not sure what exactly it is, but they're very sure that the companion star makes my correction, it says the new Chandra data shows that it changes X-ray brightness in the same manner every 28 minutes, which is likely the time it takes a companion star to make one complete orbit around the black hole. Now, that is really very fast. And the separation between the orbiting companion and the black hole is only about 2.5 times the distance between the Earth and the Moon, which is pretty close without being disrupted. Now, they're not too sure whether it's a white dwarf, material being pulled away from the black hole by the black hole and dumped into an accretion disk, or whether it is a neutron star, which is another possibility. Okay. Now, apart from that, globular clusters are always a mystery because nobody really knows how they are formed or what is their history, because the composition of the stars don't match what we know. They are basically heavy metal poor, which means that they are very poor in planetary bodies or planetary formation among the stars. So even with all the probing with the latest techniques, we are not really able to observe exoplanets within the globular clusters, and not just due to the tidal disruption that may be there, but rather due to the lack of heavy metal composition within these stars. In this case, you can see, yes, okay. It's bound together, a group of stars bound together by a common radiation, or rather a gravitational pull. And it brings to mind the tidal forces that are there, and trying to figure out the orbit of these stars about each other, among the common center and so on. And I think trying to figure out the mathematics must be really, really incredible. Now, they're found in nearly all galaxies, forming a halo around the Milky Way and other spiral galaxies. And the largest and most densest clusters compared to open clusters, which we are also familiar with, basically older and denser stars. Okay. Now, all right, coming back to that again, I just leave you with this picture. It's just so beautiful. Okay. Now, the next picture which I have is all right. This is number 15.
15 February. Yeah.
15 February, which is the Dusty Island universe. Now, this is NGC 253. Just get on to that. Sorry, give me a minute.
Share your screen.
Yes, I'm getting that. Share screen. Yes, okay.
Yeah, I can see.
Okay. It's commonly known as the silver coin galaxy for its appearance in small telescopes. You can one look at it and you can know why it's given that name. All right. It's NGC 253, which is found in the Sculptor group of galaxies. And it's stated to be very rich in dust. And you can see tendrils of dust among the spiral arms. Tendrils of dust will be rising from the galactic disk. And it's very rich with the presence of dust means there's a lot of star formation. And Circumference Messiah earning it the other name of the starburst galaxy because it's a very strong energy source of X-rays and gamma rays. Now, apart from the beauty of this picture, it was first discovered, first discovered in 1783 by the mathematician astronomer Caroline Herschel. Now, in itself, this is itself even an interesting accompaniment to this picture. Caroline Herschel, Herschel, which all of us in astronomy will know. It's the famous, same name as the famous William Herschel, who in fact was a brother, who was the founder of, who discovered Uranus using the telescope, one of the few planets, or rather the last planet discovered using a telescope. However, apart from being a sister to a very famous brother, she was in her own self a very accomplished astronomer. She's the first woman to discover a comet. She revised Flamsteed's star catalog over 20 arduous months, cataloging over 2,500 nebula and revising the stars and the catalog that he left behind. Now, initially, she was in Germany, where she was actually being groomed by her mother to be just a housewife, stay in the house and look after the house. But she followed her brother to England, and as his interest and obsession in astronomy grew, she also became interested in astronomy and was working with him, doing observations and charting the skies. Now, she was so famous that basically she was awarded, she discovered 8 comets in total, the final one in 1797. And she became so famous an astronomer in her own right that the present king of England at that time, King George III, actually paid her a salary of £50 as William's assistant. This made her the first female in Britain to earn an income for the pursuit of science. Apart from this thing, just being a scientist, she was paid for that, and as well as the first woman to earn a living from astronomy. In what do you call it? She was given a lot of accolades for her discoveries in astronomy. She completed her revision of the catalog, and she was given a gold medal from the Royal Astronomical Society in 1828. In 1835, she was only one of the first 2 women to be accepted as an honorary member of the Royal Astronomical Society. She died at a very ripe old age of 97, and during her lifetime, she received gold medals, honorary membership to the Royal Astronomical Society, honorary membership to the Royal Irish Academy, and gold medal of science from the King of Prussia. So she was a remarkable woman, and she discovered this using, as she describes it in her own words, using now let's see, where was this thing?
That was more than 200 years ago, no, Dr.
Yes.
Jiwa? Oh, incredible.
And she had a telescope which is in a Newtonian sky sweep, she called it, with a focal length of 25 inches. She doesn't give the diameter of the scope, but she used that small scope and she discovered this galaxy. So apart from it being an interesting object in its own right, the history behind the discoverer of this galaxy really caught my eye and caught my interest. Apart from that, I think my next one would be on I'm a bit
February the 18th.
oh, no, I pressed something else now. Sorry.
February 18th.
February 18, yes.
Yes.
Okay, now this one. Now, this is also a very fascinating picture. One look at it and you'll be wondering, what is it? I mean,
I call it the egg yolk nebula.
yeah. You know, it's so perfectly symmetrical with a center bulge. And this is known as a ring galaxy. This particular one was by discovered by Arthur Hogg, okay, who was a celebrated astronomer in his own right. And he was the director of stellar at Kitt Peak National Observatory. He was the director of Lowell Observatory, and as a director he retired as a director of Lowell Observatory. So basically, he was an astronomer and a physicist with quite a number of publications to his name. And he was the discoverer of this. Now, of course, at that time, we didn't look anything like this. But this is a picture which has been taken by Hubble, as well as NASA's telescopes and the European Space Agency. And it's been processed by Renoir Belanco. Who's quite famous and has done a number of processing of films in his own right. Now, is this a galaxy in the first place? Well, it is. It's a ring galaxy. And there's a question initially of what is this and what is this? And finally, well, they actually belong to the same object. Now, the interesting thing about this picture is you look down there at your lower left in this image, and you'll see another ring galaxy, a small one, which is actually not related to this, but we're actually looking at it through the intermediate zone, which is fairly transparent, right? Now, you have a ring of bright blue stars with active star formation with a denser area of much redder stars, which are much older. Okay? And there appears to be a gap. It seems to be almost transparent, clear. But I think later or more refined, this thing actually do pick up some tendrils of hydrogen gas in this zone. Okay? Now how did this come about? Okay, well, there are a few theories behind how you can get a ring galaxy. One is a collision, galactic collision, where you have a smaller galaxy colliding with a larger spiral galaxy through the center. So basically punching a hole through, and the tidal forces that cause a disruption as a sort of a wave, a shock wave that spread outwards and compresses the spiral arms of the spiral galaxy into a ring. And the inner part, of course, is composed of collisions of the stars from the smaller galaxy and the initial spiral galaxy. That is a collision theory. The other one is a disruption of the spiral arms. The arms become unstable and actually detach from the center core of the spiral galaxy and get thrown outwards, flung outwards in a shock wave, and form a circular ring around the center core, right? But in this case, from various observations that have been done in radio waves, they say that Hogg's object was not accreted from another smaller galaxy. Okay, of course, it would have happened much earlier than that, but for the past billion years or so, it hasn't been from another collision. So some say it could be due to accretion of interstellar material from around in space by either a smaller dwarf galaxy, which then this interstellar material forms an accretion ring rather than a spiral arm. Now, this is quite interesting. If you look at other images, there are other images of ring galaxies but none so perfectly round and so perfectly symmetrical as this. Most of the others are elliptical. You have the cartwheel galaxy, which has got strands radiating out from the center of the galaxy to the surrounding ring. You have rings which appear squashed, rings which appear elliptical, but nothing really like this. And this is so unique that it's been just given the name as Hog's object in honor of the astronomer Arthur Hogg. Now, my last one would be on which should be
20th of February.
of February, yes. Okay, can you see this then?
Yes.
All right. Now this is just simply incredible again. Now, this is a collision between galaxies. And every time you see, again, taken by NASA, ESA, space telescopes, and processed by many scientists and astronomers. Now, when you imagine galaxies colliding, you usually think of death, destruction, and probably stars getting destroyed. But the actual fact is, when galaxies collide, stars are born. Okay, and in this picture, you see stars are being born literally in the millions. Instead of stars being destroyed as galaxies collide, the galaxy in question here is AM 1054325. Circle each other. Their gravity and motion causes disruption of the galaxies and has actually ignited stellar creation. Now, these are all stars being born. The blue dots, the blue white dots there in the millions. Okay, and the debris stretching out from here, which is the yellowish body of AM 1054325, going on to the other galaxy, and stars are being ignited as the gravitational pull disrupt the interstellar gases and cause them to accrete and collide. Hydrogen gas surrounding the newborn stars grow pink, and the stars themselves are bright blue in this thing. And there are compact nursery of thousands to millions of stars. Okay? Some appearing, as they described here, like a string of pearls. And many of these, of course, may grow up to be globular clusters if they accrete together. In fact, there's a question whether this may even detach itself and form another galaxy by itself. Maybe a companion galaxy to whatever that's going to form here. And so what I'd like to emphasize here is that when galaxies collide, it usually isn't death and destruction, but rather the birth of new life, new stars. And I think it's just a recycling of star material and stardust, which is so important to the birth of stars and galaxies. Now, I think that's all I would like to say. If anybody would like any questions or comments to add to this, be fine.
We will look at the comment section in YouTube. At the end of the whole presentation, we see anybody post any comments, questions. Then we can answer them one by one. Yeah?
Okay.
So please let me share my screen. 16th of February, there you are. A comet, right? Okay, I'll make the picture smaller later. Structure in the tail of comet 12P Pons Brooks. So basically, this is a comet discovered in the middle of the 19th century, about 150 years ago, by two amateur astronomers, Jean-Louis Pons of France and William Robert Brooks from America. So even about 150 years ago, Dr. Jivaraj, already there's a race around the world to look for comets. So this guy Pons in France, Brooks in the USA were looking for the comet, and both of them actually found the same comet. So that's why it's named after them, right? And then because this picture taken by an American amateur astronomer, Dan Bartlett, astrophotographer. So let's look again at this thing. So it was actually what they call, in any comet you see, for example, the coma, and here you look carefully, there are two tails. There's a straight tail, which is a bit bluish, the ion tail, ion tail, an element that's lost some of the electrons around it, and there's a crooked tail called the dust tail, right? So basically, you have this. Many of the comets coma is green in color because in the coma you have the diatomic carbon. I'll give you some detailed explanation later. So basically, you have the real part of the comet, which is solid, is called the nucleus. And the nucleus is very small. So by the way, this comet could be 100,000 kilometers in diameter, no? And the comet tails, the two tails could be tens of millions of kilometers long. So what happens is that the actual solid part of the comet called the nucleus, when it's very far away from the sun, it remains at the nucleus. But when it comes within the orbit of Mars, closer to the sun, so the sun's heat and light will hit onto the nucleus of the comet. And we know that the nucleus of the comet is actually frozen dust and ice. So then the ice will sublimate. Sublimation means that it will from a frozen state to a gaseous state without going through the liquid state, right? So from the solid state, the frozen state, to the gaseous state. So that's what happened. So the material in the nucleus will sublimate, and then you have this gas cloud form around it. And then what happens is that this gas cloud is formed of diatomic carbon. I'll show you a picture of diatomic carbon. And now you have the sun's light, the UV light, for example, and also the sun's solar wind will hit and energize the carbon atoms and give off the green light. So what is this green light? It will look like this. There you are. So now you see on this first one is diatomic carbon here. All right, you see. So you have here on the right, there's a black carbon atom combined with on the left another carbon atom with a covalent bond. So you have here two covalent bonds which bind the two carbon atoms tightly. And because here the two dots on the left and on the right here means that there's another free two electrons here on the left, right? They can form more bonds later. But here, as for this diatomic carbon, there are only two bonds, the two covalent bonds in between, and it's very tight. And what happens is that the light, I go to the next picture, the light from the sun and also the solar beam from the sun will hit the carbon atoms, the diatomic carbon, and will kick out the electrons from the outer shell of the carbon atom. And as the carbon atom loses the electron, so this will become ionized state of the diatomic carbon molecule. But then later on, what happens is that the what we call the outer shells of the diatomic carbon will be filled in by the external electron will fill them again. And as they fill them again, they will give off the spectrum. Now, we don't look at the whole spectrum, we look at part of it. For example, you hear here at 450 nanometers, you have diatomic carbon spectrum. And then just above 450, you have another spectrum. And the main one is this one, about 510 nanometers. And this is the main spectrum line, that of the green line. But 510 nanometers is the green part of the color band. So this is the main part. And then of course further up you have another 2 bands of carbon. So you have 5 of the spectrum lines here. These are carbon, but the main one is 510 nanometer, which is green in color. And it's called the Swan band because the first person to study the spectrum of dielectric carbon is a Scottish scientist called Swan, right, in Scotland. So you call it the Swan brand. So the main one is here, 510 nanometer, will be this. Just a moment. Wait a moment. Not responding. Okay, so this is the part where you have the diatomic carbon giving off that 510 nanometer line, and at the same time you have the solar wind from the sun will also hit at the nucleus and hit at the coma, and because the solar wind particles are very fast, 500 kilometers per second, and will knock at the particles in the coma, and the particles in the coma will move in a straight line and give off the blue light in a straight line. This is called the ion tail, ION tail. But at the same time, the sunlight will also hit on the particles, and they call the pressure of the light radiation. So light radiation can have pressure on the dust particle, and this dust particle will move away from the coma at a slow speed. So basically you have here the ion tail, very fast, hundreds of kilometers per second, and then you have this coma which move as fast as the orbit of the comet around the sun, and then the slow one are the dust tail. So this is a part of comet Pons-Brooks, and this is a famous one because Pons and Brooks in the 19th century were the greatest comet discoverer. Every night there's a race between Pons in France and Brooks in USA. So Pons was the number one guy. He found the most comets. And then the second most comet found was by Brooks in the USA. Okay. So this is structure of the tail of comet 12P Pons-Brooks. Okay. And here they said that on April the 21st, all right, this comet will pass by perihelion. All right. And this will occur 3 days after the April the 8th total solar eclipse over America. So in April this year, many of the people in northern Mexico, USA, and eastern Canada will go gaga. Gaga over what? Total solar eclipse in the Western Hemisphere, right? So the next picture would be 14th of February. This is a nice one. Well, look at the fantastic picture. Oh, yo. I make it smaller? So the title is the Rosette Deep Field. The Rosette is of course the nebula here. All right. Rosette. And then you have here other nebulas called the Cone and Phosphor nebulas. All right. And then you have here the Rosette Nebula, and there's another object here, all right? And it's taken by our Olivier Bernard and Philip Bernhard. It looks the same guy, no. The first guy is Bernard. The second one is Bernhard. So this Olivier Bernard is actually an amateur astronomer from Belfast in Northern Ireland. And Philip Bernard is an amateur astronomer in France. So both of them took this picture, and look at it, beautiful, no? All right? Okay, now because APOD is so famous that they will never say taken by what telescope, what exposure, stacking with what software. Previously they will say, but now they assume that the audience that look at APOD are all quite expert. They don't need to look at the detail. They just have to admire the beauty of the picture here. All right. Now this is our Rosette Deep Field. All right. Very nice. So this is, remember, this is what like what we call Dr. Jiva said earlier. This is our stellar nurseries. That's new stars are being born, right? So this is this nebulae will form from the explosion of the previous stars that died, not the supernova explosion, the nova explosion. And when they exploded, the materials from the star will be thrown out during the explosion, and will collapse due to gravity, and more stars in future will be born from there. Right? So this is our Rosette Nebula. The next one is 11th of February. This is a nice one. What's this? Okay, I'll read here. Rocket plume shadow points to the moon. So basically, they never say exactly the day. In 2001, many years ago, Space Shuttle Atlantis was launched. Of course, launched from Florida, Cape Kennedy Space Flight Center, or John F. Kennedy Space Flight Center, and it was launched during evening time, and the sun is behind us, and a space shuttle, what they call Atlantis, went up into space, and that time the sun has just set, but just set below the horizon. That means further up, the sunlight can be seen. So maybe at this time, Atlantis could be, say, 10 kilometers up in the sky, in the Earth's atmosphere. So the sunlight would hit onto the plume here and cast a long shadow here. But here in the lower part of the plume, the sunlight doesn't hit. So basically, the guy who took it is our Patrick McCracken, one NASA staff. All right. Here it says Pat McCracken. Pat is actually Patrick, a man. Okay. Patrick McCracken was lucky he was there. He took the picture, and this happened that the shadow of the upper part of the smoke plume cast here, it point to go further up. Look, this looks like further down. No, actually further up, because you see the sun is already set below the western horizon, and the moon is rising up in the eastern horizon. So that means this shadow must be going up. But it go up at exact time, it point at the moon. So it was lucky. So this by a chance event, right? So this is our rocket plume's shadow points to the moon. So nice. Taken in Cape Kennedy in the year 2001 during the Atlantis Space Shuttle mission. Of course, now Space Shuttle program has been stopped already. So now we are waiting for the NASA Artemis mission next year, which will go to the moon. Okay. So now I stop my sharing now. I pass over to Yonglip. Okay, Yonglip, you're on. Yeah, we can see. Speak up, Yonglip.
Good evening. Yes. Good evening, everyone. Today I'll present the astronomical pictures of the day. So can see Dr. Chang?
Can see, can hear.
Okay. So the first image is on the 21st of February. This is the Seagull Nebula, and this is taken by Dira Venkatraman.
So we don't see the picture, Yonglip. I don't see the picture. I just see the title only. The text, astronomical picture of the day, but no picture. Maybe you go to the page itself. Go to the web page.
Can you see?
Not yet.
Okay.
Yeah. Yes. You can see on the left the picture, on the right the text.
So this is an emission nebula taken at Pinnacles National Park at California. So this object is known as IC 2177, and you see the glowing red gas over here. It's due to hydrogen gas, and this is located at the Monoceros constellation. So if you look at your star chart over here, so if you look at the Orion, near the Orion Nebula, you have the Monoceros constellation. And this nebula is also known as this Monoceros constellation is also known as the unicorn constellation. And there are many interesting objects over there. So I chose this picture is because it's quite it's one of my favorite pictures. These pictures have specific have meaning. They not only took a very nice image of the sky, but they also include the background over here. So this this is a composite image taken. There are two images over here. So a long exposure is taken on the sky, so you can see the Seagull Nebula, while on the foreground you can see the national park, and it's taken with a short exposure. So this nebula is taken it's called Seagull Nebula because of the nice wings of this nebula. And this nebula is quite a big one, so you can actually fit 5 full moons on this across this nebula. So in astronomy we have many very unique names to this nebula. They because they have certain shapes and colors. So when you come to astronomy, we have what we call the astronomical zoo. So welcome to the astronomical zoo, where you have all kinds of special nebula and special objects where you can where they are named very uniquely. So next one. So this image is taken on 13th of February, but actually this is a January full moon. It's known as a wolf moon. So this is also a composite image taken by Anthony Zagarsky. So for this image, of course, the moon is the brightest thing in the sky. So a short exposure is taken for the moon, and long exposure for the sky. So this is also a chance event because you have a like a wedge shape over here that looks like the jaws of a wolf. So he was quite lucky that day, and it forms like a shape, the shape of the wolf jaws. So it's called, and furthermore we also have the wolf moon. The full moon on January is known as the wolf moon. So I think this guy is also quite lucky. He on that specific day, he got the chance to witness this beautiful chance event. So next, I'll give a bit of history of this wolf moon. So this in the past history, people of the native tribes, they like to give this kind of moon a unique name. So for the for the full moon in January, it's known as wolf moon, and that's because the moon of January in the northern hemisphere is close is during the winter, so it's you can also call it a cold moon. So during the winter, the wolf will come out and howl. That's why they call it a wolf moon. But even on February, you can it's still winter for some northern countries, so it's known as the snow moon. Or what we have at Penang last night is the Cap Gomeh lah, the Cap Gomeh full moon. So this is taken exactly 1 month ago, and it's published on 13th of February. But I don't think that this shape has an uncanny resemblance to a very famous game. So I like to call it a Pac-Man moon.
Yes.
The Pac-Man moon. Again, it's the Astronomical Zoo. So we like to give very unique name and funny names to astronomical objects. Okay, next, it's on the 9th of February. Again, we have the Rosette Nebula. So the Rosette Nebula is known as it's a well catalog object. So if you look at the Caldwell catalog, there are around 109 objects. So for this, the Rosette Nebula is the 49th of them, and it's also located at the Monoceros constellation. So there are many interesting deep sky objects over there. So the distance is spanned. The distance to the Rosette Nebula is around 5,200 light years, and the span of the galaxy, the nebula is 50 light years. And this the apparent magnitude is around 9, so it's not visible to the naked eye.
One more thing, Yonglip, the Caldwell catalog is named after Patrick Moore, no?
Okay.
Or Sir Patrick Moore.
Okay.
So Patrick Moore started this
Patrick
catalog.
Yes.
His name, another name for him is Caldwell.
Okay, Patrick Moore. So usually when you look at this Rosette Nebula, is taken in this image. So this image is any amateur astronomer can take it. It's completely red, like this. This is due to the primary emission of the Rosette Nebula, which is hydrogen gas. So it's also an emission nebula, which means it emits light directly. And the hydrogen alpha wavelength is of course also the brightest one in astronomy. The wavelength is 656.46 nanometers in vacuum. So if you go back to your quantum mechanics, we have a hydrogen atom over here with proton and the electrons in the orbitals of the hydrogen atom. So when the electron is excited by the young stars over here, it moves to a high energy state, which is the third energy state. But when it falls back down to the ground state, you emit some of the light and release the energy back up. So for the Lyman series, you have the UV emissions, but of course we can't see UV rays. So for this very special emission, you can also have electrons falling from the third energy level back to the second energy level.
The red arrow, the red arrow.
The red arrow. So it's not a complete emission. So if you calculate the energy difference between these two energy level, it corresponds to 756 nanometers, which is which is quite interesting because it lies within the visible spectrum. But of course, if you look at this image, it's completely red. There are no other information. There are very little information you can see over here, because the hydrogen is too bright, too overpowering. So the Hubble science, the astronomers from Hubble, they are very smart. They remap the colors to make it more useful for us. So the astronomers remap the colors of the Rosette Nebula. So it's in the Rosette Nebula, other than the hydrogen gas emission, we also have oxygen emission and sulfur emission. So this is welcome to the narrowband astrophotography. For the primary emission, red for hydrogen is mapped to green. So the green you see over here is due to hydrogen, and for the sulfur, it's mapped to red. So it's less pronounced over here, but you can still see some red among the stars. For oxygen, it's mapped to blue. So you can see the blue over here is also quite pretty. So in the universe, hydrogen and oxygen are quite abundant. So you can still see some blue over here. So this is why they named it this way. These roses, yeah, it's very beautiful. If you look at it in the red spectrum, but I think this image is more characteristic of the Hubble images, because they map a narrow band onto a much wider RGB, so you can enjoy more colors this way. So these images are for us.
Yeah, one thing on the nomenclature, the way you name.
Yes.
So you see on the left, sulfur 2 filter. Sulfur 2 here in astronomy means singly ionized sulfur atom.
Okay.
Meaning sulfur has lost one electron.
Yes.
For example, you have sulfur 1. Sulfur 1 means neutral sulfur.
Neutral sulfur.
And oxygen 3 filter, oxygen 3 means doubly ionized oxygen atom, meaning an oxygen atom that has lost 2 electrons.
Yes.
For example, the most famous is called H1, hydrogen 1. Hydrogen 1 means neutral hydrogen. So that's the way they name in astronomy. So sulfur 2 here means singly ionized sulfur.
Singly ionized.
Hydrogen 3 means doubly ionized oxygen. Oxygen that has lost 2 electrons.
Interesting. Okay. So for the next image, we have one of my favorite image for today, which is a a spiral galaxy which is seen from two different wavelengths. So these images are taken by the two space telescopes we have currently, which is the Hubble Space Telescope and the James Webb Space Telescope, recently launched. So for Hubble Space Telescope, the wavelength we see is primarily in the visible spectrum and UV spectrum. But for James Webb Space Telescope, is primarily in the infrared. So I overlaid these two images together and make one of them semi-transparent, so you can see each of these two kinds of wavelengths will give you different information of the stars. Like for example, if you look at the sky, the galaxy over here, it's that you can still see some black spots over here, some black areas. But for the infrared, in the infrared spectrum, it's not empty. Actually, it's you can still see the dust over here, and this dust can only be seen with the infrared telescopes. So the infrared telescope will give you a much richer information about the galaxy. But so it's still much better to have this kind of multi-wavelength astronomy, where you can get different information with different wavelengths. So this this galaxy is known as NGC 1566 1566. So this is located in the southern hemisphere. So if you look at your star chart, for your star chart, you look at the southern circumpolar region. So at near the Dorado constellation, so it's located at the Dorado constellation near the Large Magellanic Cloud. So it's located quite far away from us. So let's analyze some of the observational data. So this galaxy is quite a nice spiral galaxy, where you have a weak bar over here, and then a very beautiful arm. And the distance is huge. So it's located 69 million light years away. So it's quite far away from us. And the redshift, the redshift is a measure of the how much the wavelength is being stretched by the expansion of the universe. So it's located quite far away from us. So that's why it has a positive redshift. So in astronomy, we know that the universe is expanding. So we are the center of the expansion. So for objects that they are further away from us, they are the expansion is actually accelerating every day. So it has a positive redshift, which is 0.005 positive. if you get a negative value, it means it's blue shifted. So in astronomy, redshift is measured by a quantity known as Z. So Z is actually the relative change of wavelength. So you compare the observed wavelength and the emitted wavelength, you get how much the galaxy is redshifted. So the redshift information gives us the how much the galaxy is moving away from us. The speed is around 0.005 c times the speed of light, which is 1,500 kilometers per second, which is in astronomy is still considered quite a manageable number, quite much more smaller. In fact, you can have numbers much greater than c. So well, the expansion of the universe is will not be limited by the speed of the universal speed of light. It can be much greater than the speed of light. So the apparent magnitude is 9.73. It's also invisible to the naked eye. So let's have a look at two different spectrum. So this is taken by Hubble, while this is taken by James Webb Space Telescope. So I think it's quite an achievement by a human being. Just I think it's launched 1 year ago. It already can take such a fantastic image of a far away galaxy. So for this galaxy, you can see some of the very young stars over here. They are taken in blue. You can see here is blue. The bluish stars. So these stars are taken by Hubble, and they are very active. It means they're active blue stars, and they are very young. For James Webb Space Telescope is in infrared, so you can see more of the gas part of the galaxy. So these gases are in the infrared spectrum. So the reason why the infrared spectrum can reveal more information to us is because this galaxy is the wavelength of this galaxy is being redshifted. Some of these wavelengths may originally be in the visible or UV ray, but due to the expansion of the universe, it's been redshifted into the infrared spectrum. So the infrared wavelength will give us the information about the dust and the stars being born. I think is more pronounced than the Hubble Space Telescope. So next, I want to investigate the mirrors of these telescopes. So, like I said just now, the blue stars will emit a lot of UV rays. So the strength of Hubble Space Telescope is in the UV spectrum. So it's it's pure aluminum. I think coated with magnesium oxide. It works on the UV spectrum, as you can see over here. For aluminum, it can also reflect quite a lot of UV rays and also visible light. That's why they choose pure aluminum. and not silver. So if you use aluminum, you can still see some of the very young stars. As for James Webb Space Telescope, it's the primary wavelength is in the infrared region. So they coated it with gold. So you can gold can reflect most of these infrared light. So the infrared spectrum is roughly around here. So gold is a good reflector of infrared light. That's why they choose to coat it with gold. So these are the two wavelength you can see by what materials they coat their mirrors with. Okay, that's all for my presentation. I'll give it to Dr. Chong.
Thank you, Yonglip.
Thank you.
So before I continue, I would like to say, so if you look at the pictures presented by Dr. Jivaraj, Yonglip, and myself, I always say the awe and wonder of the universe.
Yeah.
So sometimes when I see another totally unexpected picture in airport, the whole day I'm thinking of it. The universe is so wonderful. So basically, I would say that welcome to the wonderful universe. Not only that, like you see galaxies in collision and so on, I would say welcome to our very weird universe. We are living in a very weird universe, wonderful. And don't forget planet Earth. So the Earth itself can have awe and wonder and can be weird also. Like that Phoenix aurora seen in Iceland some years ago.
1 minute.
Yeah, just for 1 minute, okay? So now for February the 10th, all right? I'll share the screen here. Okay, February the 10th. I read the title first. The shadow of Ingenuity's damaged rotor blade. Of course, Ingenuity is a famous helicopter that is still on Mars. This was actually on the 18th of January 2024, last month. The NASA again made the Ingenuity to fly. All right. So basically, I will make it smaller here. Remember, Ingenuity was dropped from the belly of Perseverance rover a few years ago. It landed successfully on Mars, the lander, and from the lander, the Perseverance rover came out, and from the belly of Perseverance dropped up the Ingenuity helicopter. And remember, this helicopter is the first kind of flight on another planet, and because the atmosphere of Mars is very, very low, 1,000 the air pressure of that of Earth. So practically like a vacuum. So the rotor blades of the Ingenuity, they call something called Genie. Genie have to rotate very, very fast, thousands of RPM, thousands of times per minute. Then you can leave. So what happened is in January this year, last month, when it flew again successfully, when it landed, it damaged the tip of the rotor blade. Right? And that on this tip of the rotor blade, you see one part chip off. But of course, I think it's still working. So after nearly 3 years, 1,000 days on Mars, Ingenuity rover or Ingenuity helicopter or Genie is still working. All right. This is by our NASA JPL Caltech. JPL is a Jet Propulsion Laboratory, which is based in Caltech. Caltech is a famous university just outside San Diego. No, just out to the north of Los Angeles. One of the students I know from Taoist school, Prince of Wales International School, she got her first physics degree from Caltech, and of course from Ingenuity itself, the website. And so this is great. So you see here, you have this NASA rover landed on Mars 3 years ago, and from the rover, it gave birth to a helicopter which is still flying in the atmosphere of Mars. So we hope in future you have new space probes in say Jupiter or Saturn, which is the science fiction authors have been writing story for many years. In future, they have any kind of exploration of Saturn or Jupiter with what? Balloon. They will drop because the surface of Jupiter and Saturn is liquid hydrogen, liquid helium, very cold. So nowhere you can land on a solid object on the surface of Jupiter. So what do? You drop a balloon. So a balloon will float in the atmosphere of Jupiter or Saturn and take a lot of pictures. Now this is the case for Ingenuity. All right, what happened is that the chip of part of the blade of Ingenuity helicopter last month on Mars. Okay, so the next one is on the 7th of February. Again, beautiful. The heart-shaped antenna galaxy taken by Mr. Ken Briggs. He was a computer engineer from Texas, all right, Houston, Texas. And basically, similar to what Dr. Jiva showed just now, you have galaxies that can collide. Now, these are two galaxies in collision, all right? So here, I try to make it bigger. So this is during collision, and it's not only the collision. You see this tail here, stretch out the tail, millions and millions of stars. And over here, stretch out here, millions and millions of stars. All right. So remember, each galaxy can have tens of billions or hundreds of billions of galaxies of stars. So imagine 100 billion stars in galaxy A and 100 billion stars in galaxy B. They collide and it stretch out. This is after collision. And actually, when this antenna galaxies was taken many years ago, many people did simulation. Okay, you can actually simulate how the what we call two galaxies. So there are two galaxies here simulating to produce something similar to the antenna galaxy. No sound, only the visible simulation. Collide. The tail is stretching out. You see the tail stretching out? Yeah, okay. So now basically, now what I'm saying is that some people say you have galaxy A, billions of stars, galaxy B, billions of stars, and when they collide, never mind, I unshare first. When they collide, so the stars in A and B will collide, time will fall down. No. First of all, in space, there's no concept of up or down. And basically, the space in between the stars are vast, empty space. So basically, many stars in galaxy A and galaxy B, they will interpenetrate the space between the stars. Maybe out of billions of stars, a few stars will actually collide. But the other stars will interpenetrate the stars. But what's in between the stars? The gas, the hydrogen atoms, the dust. So the gas and dust can heat up the material. But the stars themselves will interpenetrate in between the space. All right. So the galaxy shape will not be affected much after one passing. But what is remaining there all the time is gravity. Gravity of galaxy A and B is always acting. So gravity of A and B as they are passing to each other, the sun will affect it. So that it will distort the shape of the galaxies. And because of the fact that many of the stars there will be stripped off and will kick out, we form the long tail like that, right? So this is it. So that's why I would like to say, Dr. Shiva, not only welcome to the awe and inspiring universe, welcome to the violent universe. We're living in the violent universe where galaxies can collide, supernova can explode, and you are orbiting near to a supermassive black hole, you can be eaten and fall inside the event horizon. So welcome to the violent universe. Okay, so this is our interacting galaxy. I'll share the screen again. February the 3rd. This is interesting. This history actually, February the 3rd is actually a view from Antares Apollo 14. I remember when the Apollo 11 landed Dr. Jiva on the moon on July 16,
69.
What they call
69.
1969. I was in high school, and I told myself, all right, never mind. I told myself that this is the time, morning, 11 a.m. Malaysian time, he has landed. But at that time, we don't have live broadcast. Only that night, 12 hours later, there's a delayed broadcast. But in the morning, in the school. I came up for my class for about 10 minutes. I said, "Has landed. We're going to see." And that night, they saw. At that time, in 1969, no color television in Malaysia, black and white, right? So we saw in black and white, all right? And then, of course, we saw the Neil Armstrong walk on the moon first time, and he spoke to President Nixon live. And that was the first time. I remember the comment made by my mother, cannot be, because the Chinese, the people, the older folks believe that you have the Chang'e moon fairy living on the moon. So modern man cannot land on the moon. But of course, never mind, let it be. So I told myself. So that was very, very important for me. And many years later, Apollo 12, Apollo 13 are not successful. Apollo 14 landed. Okay. So this was the case for Apollo 14. Can see the picture?
Yes.
Okay. So basically, is that you have this small kind of rover. They call it the what they call this. This is a small rover here, and then very far away, there's a rock here, okay, called Turtle Rock. And basically, the two astronauts on the surface, one is Edgar Mitchell, who took this picture from the lunar module, which is called the Antares, not the star in Scorpio, the lunar lander Antares, where the Edgar Mitchell and Alan Shepard there. So later on, when Alan Shepard came down, I remember he played golf. He put a golf ball and a golf stick. He hit the ball. He flew into the distance. And remember, with the moon's 1/6 gravity, the golf ball that you hit will go very, very far. It will hit at full swing on the moon. The golf ball can fly many kilometers from the place where you hit it. Okay, but when he took this picture, this what they call Edgar Mitchell also threw a kind of a long stick, a spade, and you see the spade fell somewhere there, near to the Turtle Rock there. All right, and the golf ball that hit by Alan Shepard fell near there. All right, so next year in future, if mankind go back to the moon, all these objects will be there. So because the moon doesn't have an atmosphere, it's like a pure vacuum. So what happens is only the solar wind, the ionized particle from the sun that hits the moon's surface, and the micrometeorites. But basically, whatever moon footstep on the moon or any object on the moon will never change that for millions of years, right? So this is Apollo 14 on the moon, all right, taken by Edgar Mitchell, was in the lunar lander, all right. So the last one will be February the 2nd. Nice one. NGC 1893 and tadpoles of IC 410. So actually, in astronomy, we have this thing called New General Catalog. Actually, there's nothing new in NGC. NGC more than 100 years old. So they shouldn't call it New General Catalog. But because the tradition stay, we still use the word New General Catalog 1893. And IC here, it's not our identity card, index catalog. Right? So you have this whole nebula is called the NGC 1893, and this IC 410 is this. Okay, and then they use here the term here. This is taken by our Sander de Jong. So in English speaking, Malaysians don't know de Jong. They will say de Jong. No, this is a Dutch guy from Holland. So we say Sander de Jong. The J become a Y. The Jong. Okay, just like Jonkers Walk becomes Jonkers Walk in Malacca, right? So taken by Sander de Jong from the Netherlands, Holland, and this is a beautiful nebula plus the index catalog object. So basically, they call this one the tadpoles. I enlarge it now. Now remember, this object, which is explained by Dr. Jiba earlier in his picture, and this Yonglin, that can be very large. It can be many of light years across. So these tadpoles are what I call what? Stellar nursery. So basically, it's like this. You have this whole nebula here, plus the two tadpoles formed earlier, right? And many of the stars here grew old and died. And the younger stars here are blocked by this dust cloud. So behind these dust clouds are very bright stars, young stars, and they give out a lot of light. And the light here will energize this dust cloud here and brighten it up. and because the black stars here, the stellar wind is much stronger than our solar wind. You know, our solar wind is just a normal breeze, although the solar wind particle travel at 500 kilometers per second, but because the number of particles per unit area is very small, so the pressure is here it could be like hurricane force. So the stellar wind is very hard. They will blow away, and the way they use the word, the scientists use the word evaporate. So they evaporate this dust cloud until many years later, the evaporation will make the whole dust cloud disappear. Now remember, the head of this tadpole could be half a light year, and this what they call tail of this tadpole could be 2 light years. But if you wait for millions of years, the whole tadpole will be blown away to nothing. All right. So basically, the thing is this: there are 2 processes happening here. Some stars are forming inside the tadpole, and you give them enough time to form successfully. So the clouds of gas and dust will collapse due to gravity, and the time will come that the pressure in the center of the dust cloud will reach ignition, where hydrogen will be fused to helium. Then the star is born, all right? And then the star will be successfully born. But what happens in this case is that suppose this star is in the process of being born, but the stellar wind is very powerful, it will blow away the whole dust cloud before the star was born. So what is this called? I will call it a stellar miscarriage. So it doesn't mean that you see a lot of tadpoles in space, or stars will be born. Stars will definitely be born. No, only 50% chance that a star, a planet, the aliens can be born. 50% chance that the clouds, dust cloud will be blown away, so the star will be not be successfully born. So we don't know what's the case for this. It can be born successfully in future, or it may not be born. It may be a stellar miscarriage. So basically, our whole solar system, the atoms in your body, the air you breathe now, you are sitting on the chair, they're made of iron, let's say. They're sitting on the ground, made of silicon, the cement floor, all right? They are from a protosolar nebula that collapsed. So maybe our solar system was born from a tadpole earlier, a tadpole. So this tadpole may form a solar system similar to our sun years later, all right? So this is from the NGC 1893 and tadpoles of IC 410. Okay, so now I stop my presentation now, and we have any final comments from our presenter? So any final comments, Dr. Jivash, Yonglip? So what do you think? So when I started subscribing to Sky and Telescope magazine, Astronomical magazine in the 1980s, each time I opened the magazine, I say, so nice, the whole day, kept thinking of some images, right? But now more. Now you have video. You have video changing images and sound also. Fantastic. Any comments? Now you look at, because Facebook, you have some technical issue. You look at YouTube channel. Any questions? Any comment? I don't see any comments in the YouTube channel. Okay. Any final thoughts, Dr. Jiwa? Yongdi?
No, just the advances in astrophotography is incredible.
Yes.
I remember those days with the film camera, ASA 800, ASA 400.
Yeah.
And we are so thrilled by it.
Now you have ASA 100,000.
Yeah, exactly. Now you have ASA 500,000 electronic pictures without actually developing. Whenever I take my film rolls to the camera shop, I have to tell him, no, all the small dots, you please develop for me. Don't say nothing there. The first time I sent, he said, nothing, cannot see anything. I said, no, you just develop. Don't worry, I got something inside there.
Fantastic. You remind me, I think about 9 years ago, I and Chun Kiat, our member, and of course his father, Mr. Lim, and the mother, we were invited to an event in Johor Bahru town, city. All right. So in the city there outside, there's a kind of a school, all right, at night. And I think that time our CK Chun Kiat bought his new, I think Sony camera or Canon. I think Sony, with a very high ISO number. He said to the next day, he said, Doctor, I'll show you something. He took me to a classroom in the school at night, and we put our head inside. You know what I saw in the classroom? Nothing, totally dark. Outside was dark, inside dark. He took a snap with the camera. He came out and he enhanced it. You can see the chair, the table, and the poster in the classroom clearly. I couldn't see with my eye. I told myself, technology is incredible. You can see nothing with your eye. Our human eye is so inefficient. But with the camera, you take it and you enhance it. It's so as clear as daylight.
Yes.
That means next time you take a picture, study it. 101 information is there. Don't miss it out. Yeah, fantastic. Yeah. So okay,
Okay.
Any other further comment? Okay. So I'd like to thank very much to our Michael for hosting tonight's event, APOD show. We wait for the next one at the end of March. And of course, our Mr. Lai, who selected the pictures. All right. So of course, we hope our same presenters again, and also maybe we can ask more of our presenters to come and enjoy their presentation. So for example, I tell myself when I give a talk to the member public, I'm actually inside bursting with information excitement. I want to share my excitement astronomy with any person that I can meet. Right? So thank you very much.
Okay.
Thank you, Dr. Jiwalash. Thank you, Yongdip.
Thank
Meet
you.
again. Thank you.
Thank you, Dr. Chong.
Okay.
Thank you, Dr. Chang.